Hi, this is John Whitaker for the Mathematical Analysis 2 class, and this is our 14th lecture, and we're still working with Riemann-Stieltjes integrability. And here's a nice theorem. It says if f is Riemann-Stieltjes integral with respect to alpha, and G is also Riemann-Stieltjes integrable with respect to alpha on A to B, then part A is that f times G is Riemann-Stieltjes integral, and the absolute value of f is Riemann-Stieltjes integral, and that's the value of the Riemann-Stieltjes integral of f d alpha is going to be less than or equal to the Riemann-Stieltjes integral of the absolute value of f with respect to alpha. Proof. We let f be Riemann-Stieltjes integral and G be Riemann-Stieltjes integral on A to B. And then we want to prove part A. That is, we want to show f times G is Riemann-Stieltjes integral with respect to alpha. Okay. And so what we do, it's a very nice trick here, we consider this function phi of t being equal to t squared. Okay. Then we notice that this is continuous. So t squared is continuous. So that means that phi composed with f is Riemann-Stieltjes integral. But let's say what that is. That's equal to f squared is Riemann-Stieltjes integral with respect to alpha. Okay. And that's because of the continuity and f being Riemann-Stieltjes integral. We had a composition of a continuous function with a Riemann-Stieltjes integral function creates a Riemann-Stieltjes integral function. That's what we have. So what this says is if f is Riemann-Stieltjes integral, then f squared is Riemann-Stieltjes integral. Let's write it down before we prove it. Okay. Since f and g are both Riemann-Stieltjes integral functions, then f plus g and minus g and f minus g are all Riemann-Stieltjes integral functions. They're all in the collection of Riemann-Stieltjes integral functions on alpha with respect to alpha. So what we have is that f plus g squared, that's going to be Riemann-Stieltjes integral. And then if we subtract from that f minus g squared, f minus g b squared is Riemann-Stieltjes interval. And the subtraction between two Riemann-Stieltjes interval functions is Riemann-Stieltjes interval. Because you can think of this as the addition of -1 times this function. So let's look at this. F plus g squared minus f minus g squared. Well, that's equal to f squared plus 2fg plus g squared minus f squared. Then it would be plus 2fg, and then it would be minus g squared, which is equal to 4 times f times g. And this has got to be a Riemann-Stieltjes integral function. So we multiply that by a constant, 1/4 times 4 times fg equals to fg. This is going to be Riemann-Stieltjes integral. I'm going to prove it if you multiply a Riemann-Stieltjes integral function by a constant. The output is Riemann-Stieltjes integral. So that's what we have. That's the proof of part A. Proof of part B. What we do is we consider phi of t being equal to the absolute value of t, which is continuous. Since f is Riemann-Stieltjes interval, then phi of f, which equals to which equals to the absolute value of phi, is Riemann-Stieltjes interval with respect to alpha. Okay. Depending upon what f is, really, is depending upon what the Riemann-Stieltjes integral of f is. So we let c be equal to 1 or minus 1, such that the absolute value from a to b of f d alpha. Now look, this integral is a number. We're taking the absolute value. That's either equal to this integral or minus this integral. So I'm going to say, well, it's equal to c times this integral. And it's either plus or minus 1, whichever it is. And of course, we bring that constant inside. That's something we've learned. Properties of Riemann-Stieltjes integral function. And then this guy right here is nothing more than, this is nothing more than the absolute value of f, the alpha. That's what we have. Or I should say it's less than, not equal to, less than. And that's because c times f is definitely going to be less than or equal to the absolute value of c times f, which is just equal to the absolute value of f. And we've already had a statement about if you take the integral of something smaller and compare it to the integral of a bigger function, the integral of the bigger function is bigger than the integral of the smaller one. Okay. Here's a definition. The unit step function I is defined by so I of x is equal to, well, it's one of two things. It's piecewise defined. It's I if x is less than or equal to 0, and it's going to be 1 if x is bigger than 0. So we're going to be working with this unit step function. One thing I want to tell you is that we haven't really calculated any Riemann-Stieltjes intervals. Not one. We've got properties for them, but we haven't computed one. You know, we worked with derivatives, and we computed some derivatives. Okay? But here, we haven't computed any Riemann-Stieltjes interval. What we're going to do is kind of get in a situation where we can compute at least some Riemann-Stieltjes interval. And so here's the theorem that will help us with that, progress us towards that. Here's what it says. It says, if A is less than S is less than B, F is bounded on A to B, F is continuous at S, and we're going to find this alpha of x to be equal to I of x minus s, then the interval from A to B of f d alpha is equal to f of s. Okay, let's look at the proof. We let A be less than S be less than D. F be bounded on A to B. F be continuous at S. And alpha of x equal to this unit step function acting on x minus s. I'm going to look at this guy too. Look at this guy first, so this alpha. Now, alpha of x, that's going to be defined to be equal to 0, and that happens if x is bigger, if less than or equal to s, or I should say x minus s, is less than or equal to 0. And it's 1 if x minus s is bigger than 0. And that's the same thing as being equal to 0 if x is less than or equal to s, and 1 if x is bigger than s. So that's the opposite of x. We can see that that's monotonic because it's 0 a lot of times. So as you take small x values, they stay 0 up to s, progressing. And then after you get bigger than s, it jumps up to 1. So it's this constantly 0 function jumps up to 1 beyond s. And so as you see by the graph, it's increasing, monotonically increasing. Okay. Now, what we're going to first do is show that f is integrable with respect to this alpha. And so we let epsilon be greater than 0 be given. As I write this down, the proof in the book is fairly short. I've added a good bit of details, maybe too many details, but here's what they do. And this is what's in the book, we consider the partitions of the form P equal to x of 0, x of 1, x of 2, x of 3. So it's only got these 4 entries where, or with, x of 0, of course, is going to be A. We're doing a partition. X of 1 is equal to S, which is less than x of 2, which is less than x of 3, which equals to B. Then, if we look at this upper sum, P, F, alpha, these types of partitions, that's going to be, I'm going to take my time here. So sum as I runs from 1 to 3, in this case, of the big n sub I, so the and supremum values over the subintervals. Delta alpha I, okay? And that's going to be equal to, so I'm going to expand this sum. It's n sub 1 times the alpha of x sub 1 minus alpha of x sub 0 plus m sub 2 alpha of x sub 2 minus alpha of x sub 1 plus m sub 3 times alpha of x sub 3 minus alpha of x sub 2. Okay. Okay, what is alpha of x sub 1? Well, it's 0. And that's because x sub 1 is s, and s is less than or equal to s. So this is m sub 1 times 0. X sub 0 is a, it is definitely less than s, so that's 0. Plus m sub 2. Alpha x sub 2 is bigger than s, so that's 1 minus 0, and that's s here. And then plus m sub 3. Now alpha x sub 3 is b, that's bigger than s, so we get out alpha of b, we get out 1 minus, but x sub 2 is also bigger than s, so alpha of it is 1. And so this is equal to m sub 2. Similarly, the lower sums, well, I'll say that it's just going to be equal to that little m sub 2, which was the themum over the interval between x sub 1 and x sub 2, okay? Same way as what I did before. Well, since f is continuous at c, I'm sorry, at s, there exists a delta bigger than 0. Now I'm going to put another restriction on delta, and delta is going to be less than b minus s over 2, so the distance between b and s divided in half, such that for all, and I'm going to write it down this way, x sub 2, element of a to b, with the absolute value of x sub 2 minus s being less than delta, then the absolute value of f of x sub 2 minus f of x sub 2 here, minus f of s, and that's going to be less than epsilon. And I'm not I'm not just gonna pick epsilon, I'm gonna pick epsilon over 2. It'll be less than any positive number, as long as I pick the right delta. I can pick the right delta for any positive number. I picked epsilon over 2 to be the number. So, for all x sub 2 element of A to B with absolute value x sub 2 minus f less than this delta, here's what we have. A series of things. We have minus epsilon over 2. It's going to be less than f of x sub 2 minus f of s, which is going to be less than epsilon over 2. That's just working with that statement involving absolute values that we get from continuity. Then I'm going to add f of s both sides. So this implies that minus epsilon over 2 plus f of s is going to be less than f of x sub 2, is going to be less than epsilon over 2 plus f of s. So, for all x element of s up to s plus delta this is still in A to B because of our choice of delta. And what we have is minus epsilon over 2 plus f of s is going to be less than f of x sub 2, which will be less than epsilon over 2 plus f of s. So, what this tells us is that the little m sub 2, which equals to the infimum over, here it's going to be s to x sub 2, then x sub 1, but that's just s. That's going to be greater than or equal to minus epsilon over 2 plus f of s. Look, all of these guys, for all the x's in here, and here I should just have x. Okay. For all the x's in here, we have this result. And so if you take the infimum of these guys, it's definitely going to be bigger than or equal to this guy, which is the lower bound. And similarly, the maximum, the m sub 2, which equals to this suit, not max, suit from s up to x sub 2 over that interval. Okay, that is going to be less than or equal to epsilon over 2 plus f of s, which is what's written right here. Okay, thus the upper sums such partitions minus the lower sums of such partitions is equal to m sub 2 minus little m sub 2, which is going to be less than epsilon. So as I was saying, we're trying to prove that we can integrate this first of all. And so we can, because of that often used fact we have for integrability, for Riemann-Stieltjes integrability for F. So F is Riemann-Stieltjes integrable with respect to alpha. Now, also, for all the partitions, of the form P equal to this x0, x1, x2, x3 with x0 equaling A less x2, I'm sorry, x1 equaling S less than x2, which equals, I'm sorry, which is less than x3, which equals to B. We see that these upper sums with such partitions is less than or equal to epsilon over 2 plus f of s. Now this is true for, here's what I'll say, writing it kind of using words here, for x sub 2 here, close to S. What we mean by that is within delta units. So, here's what I have. The integral from A to B of f d alpha is equal to the infimum over all partitions of these upper sums, okay? And so that infimum's got to be less than this guy. Epsilon of 2 plus f of s. Well, we could say the same thing, or a similar statement with the lower sums. So, since minus epsilon of 2 plus f of s is less than or equal to the lower sums, I'm sorry, yeah, the lower sums of alpha, for x of 2 close to s, again, what do we mean there? We mean within delta units of S. Then what we have is minus epsilon over 2 plus f of s is definitely going to be less than or equal to the supremum over all partitions of these lower sums, which equals to, of course, the integral from A to B of f d alpha. And so, combining two of these statements here, we have minus epsilon over 2 plus f of s is less than or equal to the integral from A to B of f d alpha, which will be less than or equal to epsilon over 2 plus f of s. And so since epsilon greater than 0 is arbitrary, what we get is that the integral must be equal to f of s, and that's the proof. Excuse me. Next thing I want to do is talk about a sequence. A series. A series. This was really in a previous chapter of our book that I chose not to cover. I'm going to do just a little bit of things here, and hopefully, if we have time, we'll go back to series and look at them a little bit more closely. If we have time later in the course, that's my plan. But here's the definition. It says, given a sequence of real numbers, we'll call them A sub n. Then the infinite series of this sequence A sub n is, well, it's this series, summation here, as we'll say, n runs from 1 to infinity of A sub n, which really equals to the sum of A sub 1 plus A sub 2 plus, and it goes on forever. Okay, as a definition, associated to a series of real numbers is a sequence of real numbers S sub n, which really is equal to, it's the finite sum, here I'll index it with k, up to n of the sequence involved in the series that we're adding up. I'll write on A sub k. And this is known where this series S of n is called the sequence of partial sums. It's the sequence of partial, when we're going to 10, sums. Here's a definition. An infinite series of real numbers and let's denote it by n running from 1 to infinity of A sub n, converges to a number, to S, if the sequence of partial sums converges to S. saying that the limit is n goes to infinity of s of n equals to this number s. If the limit as n goes to infinity of s of n does not exist, then, so if the sequence of partial sums does not converge, then we say that this sum, from which we got the sequence of partial sum, diverges. I'd like to look at two examples. Okay, so our first example, we take a look at the sum as n runs from 1 to infinity of 1 over n times n plus 1. So can be rewritten as n runs from 1 to infinity of 1 over n minus 1 over n plus 1. You quickly see that this fraction combines to get this one. Okay. So, if you will, if you look at the s of n, the nth term of partial sums, this will be equal to the sum, maybe k runs from 1 to n, of 1 over k minus 1 over k plus 1. Now, s of 1 then will be equal to 1 over 1 minus 1 over 2. S of 2 will be what I get when we run from k running from 1 to 2. That's 1 over 1 minus 1 over 2. And then plus what I get when k is equal to 2. So that'd be 1 over 2 plus 1 over 3, which equals to 1, this is minus here, minus 1 over 3. S of 3, that's going to be equal to 1 minus 1 over 3. That's when you add the first two together, plus what I get when I have n be equal to 3. Then I'd have 1/3 minus 1/4, which equals to 1 minus 1 over 4. In general, I'll work right here. S of n is going to be equal to 1 minus 1 over n plus 1. So the limit as n goes to infinity of s of n equals to the limit as n goes to infinity of 1 minus 1 over n plus 1, which equals to 1. So that means that our sum, our series, as n runs from 1 to infinity of 1 over n times n plus 1 converges to 1. This is something you see in a normal calculus class. I just wanted to get us a reminder, and I want to do one more example. So as another example, I have the sum as n runs from 1 to infinity of minus 1 to n. Okay, and so note that s of n is going to be equal to the sum as k runs from 1 to n of minus 1 to k. And so s of 1, well, that's definitely going to be minus 1. S of 2 is going to be minus 1 plus 1. Minus 1 squared is plus 1. That's 0. S of 3, minus 1 plus 1 minus 1, which equals to minus 1. in general, we have s sub n is going to be equal to minus 1 if n is odd, and 0 if n is even. And the limit, as n goes to infinity of s of n, does not exist. And so, that says the sum, as n runs from 1 to infinity, of minus 1 to n, diverges. Next thing I want to do is very quickly put up a theorem that's an extension of the previous theorem that we had. It's this theorem. Suppose C sub n is greater than or equal to 0, and that's for n equal to 1, 2, whatever. And the sum, as n runs from 1 to infinity of C sub n, that this is a convergent series. Then we're going to have the sequence. S sub n is a sequence of distinct points and we're going to open interval from A to B, where our function we're about to get to is defined. And the function is going to define the closed interval. And we're going to find alpha of x to be equal to the sum as n runs from 1 to infinity of C sub n times this unit step function I of x minus s sub n, so much like what we had for the previous theorem. And then we're going to let f be continuous on the closed interval from A to B. Then our conclusion is that the interval from A to B of f d alpha is equal to the sum, as n runs from 1 to infinity, of C sub n times f of s sub n. Okay, one thing I want to tell you is that this is supposed to be a number. It is a number. And the reason it's a number is the f of s sub n's, they're going to be less than or equal to some fixed number. And so this whole sum is going to be less than some number. And I can show that this guy, if you pull it out, we're just looking at the sum of the f, the sum of the C sub n. But really, that's not something we're going to concentrate on. I don't think I'm going to get through all this theorem's proof, but I'm going to get us started. And what I'm going to say, just to get us started, we'll quick with this and start here next time. It says for each fixed x element of A to B, the sum, as n runs from 1 to infinity, of C sub n excuse me, I of x minus s of n is a convergent series. And really that's true because this guy right here is either 0 or 1. So this sum is going to be less than or equal to the sum of all the C sub n's. Okay? And so since this is a positive number, it's an increasing it's an increasing sequence, the partial sums are, that's going to be bounded by the C sub n's additions. And so by the monotone convergence theorem, this has to converge. Okay, here, the last thing I'll say is if we let x sub 1 be less than x sub 2, then for each n, we have 0 is less than or equal to I of x sub 1 minus s sub n, which will be less than or equal to I of x sub 2 minus s sub n. So x sub 1 is smaller than x sub 2, so if we push further along and have a bigger thing minus s sub n, that's, as we said, for I was 0 most of the time and then jumped up to 1. So if you push further along, you know that you're going to be bigger than or equal to where you were. And so since C sub n is greater than or equal to 0, then C sub n times I x sub 1 minus s sub n is going to be less than or equal to C sub n times I x sub 2 minus s sub n. And so, final thing I'll write is that the alpha of x sub 1 is going to be equal to this sum, n running from 1 to infinity, of C sub n I of x sub 1 minus s sub n, which is going to be less than or equal to the sum as n runs from 1 to infinity of C sub n I x sub 2 minus s sub n, and that's equal to the alpha of x sub 2. And what that shows is that alpha is a monotonically increasing function. We'll stop there. I'll write up what I have again when we start the next lecture, but that ends lecture 14 now. Thank you very much.